In this video, I'm going to show you how to find the limit of some special trig functions. Not the basic trig functions, where we can just plug in a number 4x, but what happens when x approaches 0 and then 0 is actually in the denominator of the function. So to do this, we need to recall two theorems, and the first one is the limit of sine x divided by x as x approaches 0 is equal to 1. And then the other one is the limit of 1 minus cos x, all divided by x, as x approaches 0, this equals 0. Now you should have these memorized to make it easier for you to do the limits a little bit quicker. All right, so this first example here, I can see that I have a sine 2x, and I'm going to use my double angle identity to expand this to be 2 times sine x times cos x all over x. And then what I'm going to do is I'm going to separate this into little parts. So the 2 we can ignore, so I'm going to bring that to the front. So I have 2 times the limit of as x approaches 0. And then I'm going to take the sine x and x and put that together. And then I'm going to move the limit through, so I'm also going to find the limit of cos x as x approaches 0. All right, so this first part here, using my theorem, I know that's going to be 1. So I have 2 times 1 times, and then in the second piece where I have cos x, if I look at the graph of cos x, as x approaches 0, I can see that I'm approaching the value of 1. So now I have 2 times 1, which equals 2. Now I'm going to show you a different method to find this. And the reason for this is actually a very useful method for different other types of examples that you will see later. So what I'm going to do is I'm going to start with my expression. I'm going to multiply the top and the bottom by 2. And when I do this, I get the limit. Oh, I forgot something. I forgot the word sine. So let's squeeze that in here. So I now have 2 times sine 2x, all divided by 2x. And what I'm going to do now is I'm going to say that let theta equal 2x. So if x approaches 0, which is what's happening here, then 2x approaches 0. Now if 2x is approaching 0, then theta also approaches 0. So I'm going to rewrite this now as the limit of theta approaching 0, and this will now be 2 times sine theta all over theta. And now I can move the 2 to the front, so I have 2 times the limit of sine theta over theta as theta approaches 0. And then we know that this is 1 from the theorem. So I have 2 times 1, and that equals 2, which you can see is the same as my first part, which I did, my first method. All right, let me show you another example. And in this example, we're going to actually use this concept which I just showed you here on the right side. So I have sine 2x over sine 3x. Now, instead of actually expanding, I'm actually going to do this multiplication here. And actually, I can't expand sine 3x. There isn't any identity that we've already learned or that we know that we can do this. So I'm going to multiply the top and the bottom by 2x. And I'm also going to multiply it by 3x. And you'll see why when I reorganize all of this. So what I want to do is I want to line up the sine 2x, and I want to join it with this 2x in the bottom, times, and I want to join the 3x over here with this sine x over there. So I have a 3x in the numerator and a sine 3x in the denominator. And then what I have left is a 2x on the top and a 3x on the bottom. All right, so using my let, which I'm actually not going to I don't need you to do this anymore since I've already shown you this, we know that the limit of sine 2x over 2x is the same as just saying the limit of sine theta over theta, which equals 1. So this part we have is 1. this green part, 3x over sine 3x, that is also equal to 1. And we can apply the same method that we did here on the right side, where theta is equal to 2x. Now we can say theta equals 3x. So this is also 1. And then the last part here is that the x's here in the last fraction, they cancel off. So I have left 2/3. So 1 times 1 times 2/3 gives me 2/3. All right, I want to show you one more. This one, part C, we can look at in class. Now to do this one, in case you've forgotten, there's a couple of useful trig identities. And we're going to apply the second one here, where sine squared x plus cos squared x equals 1, the Pythagorean identity here. So we also know that I can rewrite this as over x squared as x approaches 0. So if I replace the 1 in the denominator here with sine squared x plus cos squared x, let's extend my line, I can see that my cos squared x's cancel off. So I just have the limit of x squared over sine squared x as x approaches 0. Now, what I can do is I can expand this. So I have the limit of x as x approaches 0. So x squared is the same as x times x. And then sine squared x is the same as sine x times sine x. So I can actually split this up into 2 separate fractions like this. And each of these individual ones we know as the limit of x approaches 0 is equal to 1. So this will be 1 times 1, and this will give me 1. So I've shown you some examples, so let's see if you could try some of them on your own.